Today we're going to start on Chapter 2. In this chapter, we're going to start some actual calculus and develop a tool that will allow us to talk about the steepness of a graph. Let's look at a simple example. We'll take a function, f of x equals just x squared. We know what that function looks like, but we're going to go ahead and graph it, just so we can get an accurate graph of what we're dealing with. If we look at various points on this graph, I'm just going to go ahead and take the points 1, 1, because that's a nice, easy point. I'm going to go ahead and pick another point, 1/2, 1/4. So 1/4 is the square of 1/2, so it's a point on this graph. I'll zoom in on those. When we graph these, we can get the sense that the graph is that a parabola here is actually steeper up here at 1, 1 at point A than it is down here at point B. But that's kind of just a gut feeling. What we want to be able to do is mathematically say for sure that one is steeper than the other. The way we're going to do this is by trying to approximate the graph of this function, at least at a point, with a line that comes the closest to agreeing with the function near that point. For example, if I plot the line y equals 2x minus 1, that line passes through the point A, the point 1, 1, and it looks very, very close to the parabola. It agrees with that parabola near that point 1, 1 extremely well. We call such a line a tangent line to the curve at that point. And you might have heard of tangent lines before. You might have seen them in a geometry class where you're dealing with a circle. When we have a circle and a point on that circle, we can have a tangent line to that circle. Let's move that over there so it doesn't interfere with over here. But we would define a tangent line to the circle through a point as being a line that only hits that circle at one point. Unfortunately, that concept of tangent lines, that definition at least, is not enough for what we need to use it for. Let's look at a slightly different example. I'm going to look at x cubed minus x. We have this graph here. I'm going to zoom in to where most of the action is actually happening. And I'm going to also put the point negative 1/3, comma 8/27. So that's what I get if I plug negative 1/3 into my function. I get this point up here. It turns out that there is a tangent line to this curve at the point A, and that tangent line actually looks like y equals negative 2/3 x plus 2/27. So you can see here that it does just touch that graph at that point, and it does seem to agree, at least when you're really close to A, with that curve. Unfortunately, we have another point over here where that line does hit our graph. So we can't just say that our tangent lines can only hit the graph at one point, but at least when we're close to the point that we're talking about, or this point A, in that region, it only hits at one point. That's kind of the idea we want to have. But really, we had to overlook these extra intersection points because approximating that curve at least near the point is the important feature that we want to capture, and not the idea of only hitting the graph once. So let's go ahead and put in for our function here the fact that or at least that I found the tangent line at 1, 1 to be the line y equals 2x minus 1. Of course, throughout this section, I'll show you how we got that answer. Though for the moment, just take my word for it. We can also look for our tangent at our other point. So at 1/2, 1/4. If we go back to our graph here, I'm going to go ahead and plot the line y equals x minus a quarter, and that line actually will hit at B, and only at B, and it's going to be the tangent line at that point. Again, how I actually got that, we'll get to through the course of this section. So let's go ahead and put that in here. Y equals x minus 1/4. If we want to compare the steepness of our curve, what we're really looking at is what is the slope of these lines. Up here at A, our tangent line has a much steeper slope, a much bigger slope than our slope for our tangent line at B. In fact, the slope here was 2, the slope here is 1. And so you can even say that the slope is twice as big at A than it was for B. So I could essentially say that our steepness is the slope of a tangent line. Slope of tangent line. And we want to get a formal way of actually finding out what those slopes really are. How would we actually find those tangent lines and their slopes? Well, normally when we find a line, we need to have two pieces of information. That could be a slope and a point. It could be 2 points, in which case we could use those 2 points to get the slope and work from there. But we can't get a line with just one piece of information. So say here at A, if all I know is that we're dealing with the point 1, 1, that doesn't tell me nearly enough to tell me what the line should be. I would need the slope, or I'd need to have some other point. But in this case, our tangent line doesn't ever hit our curve ever again. We can't pick another point on our curve to give us to find the slope of this tangent line. So we're going to have to do something a little bit different. In fact, what we're going to do is we're going to pick other points that are on the curve to get some lines that are not quite tangent, and use those as a way to get to the tangent line. So I'm going to go ahead and take out the point B for now. We don't really need that for going forward. Let's say we take a point. Actually, I guess we can go ahead and use the point B for what we're going to do for the moment. I'm going to draw a line from A to B. This is not a tangent line to our curve because it does not follow the curve at either one of these points. It just connects 2 points on the curve. We call such a curve, or such a line, a secant line. So I can say here, the secant it's a line connecting 2 points on a curve. Let's actually get a little bit more formal about it. Let's say we have 2 points. We have x, comma, f of x. So here, just some x that we're using. In our example, we're using 1 for that. Then what is the value of the function at 1? In this particular case, that's just 1 as well. So this point A here is 1 comma f of 1, where f is x squared. We're going to take this x that we're putting in here, and we're going to modify it slightly. We're going to add or subtract a tiny amount. In some books, we use the letter h for this, but our book goes ahead and uses the notation of delta x here. So remember, we talked about delta x as being a difference in x's. You can also call it a change in x's. So we're basically taking x and we're giving it a tiny little change. But then we're going to take this value and we're going to plug it into the function. That gives us another point on the curve, and if delta x is small, then that's a point that's relatively close to the one we're trying to work with. Let's go back to our picture here, and now I'm actually going to go ahead and get rid of b. I don't really need it now. And what I'm going to do instead is I'm going to make what we call a slider. I'm going to go ahead and call this h. And I'm just going to give it, allow it to vary between -1 and 1. I'm going to give it a small increment so it can actually show me a lot of values. And what I'm going to do is I'm going to make a new point based off of the 1, 1 that we have here. So I'm going to take 1 plus this little h. That's going to be my x coordinate. I then need to go ahead and plug 1 plus h into my function. GeoGebra actually allows me to go ahead and use f of 1 plus h, and it will calculate that value for us. And that gives me a point b. And the point of using a slider here is I can move that point around to my liking. So if h is -1, then we're looking at the point 0, 0, because, well, 1 minus 1 is 0. But we always get points on this curve. I'm now going to go ahead and connect a to that b. And as I move my h value, it moves that secant line. And notice that when I get really close to h equals 0, in fact, when h does equal 0, we have a big problem here because we don't have two different points. But if we're dealing with points that are close to 0, h's that are close to 0, our secant line is very close to the tangent line that I told us about before, that y equals 2x minus 1. And so that's the idea. We essentially want to look at secant lines where the points are really close together and get the tangent line as the approximation to those secant lines. Of course, we're interested mostly in what is the slope of those lines. And once we have these two particular expressions here for our points, we can go ahead and write down a formula for our slope. Our slope is a difference in our y values. Our y values here are f of x and f of x plus delta x. I'm going to go ahead and put the f of x plus delta x first, because it's kind of standard to do so. So that's the difference in our y values. Our x values are x and x plus delta x. I do need to make sure I put them in the same order. So since I put f of x plus delta x first, I need to put x plus delta x first here. But now, the bottom actually does simplify slightly. We can cancel out the two x's. So we just get f of x plus delta x minus f of x divided by delta x. That is the slope of the secant line. And as we let this delta x get smaller, we get closer and closer to being a tangent line. Of course, we can't ever let delta x be 0, both because then we wouldn't be dealing with two different points, but also because this formula would break. We'd be dividing by 0. But we can, instead, look at the limit. We can say that the slope of the graph is the limit as delta x goes to 0 of this expression here. If that limit exists, then that's going to be the slope of our tangent lines. Now, in our particular example of of x squared and x equals 1, we can go ahead and find this limit by hand. So we're taking the limit as delta x goes to 0. That part's always exactly the same, but don't forget it. We're going to replace the f with our expression for x squared. Basically, I'm just going to put what we have inside here in with a square on it. Of course, I'm going to go ahead and replace the x's with 1. So we get 1 plus delta x squared minus f of 1, because x is going to equal 1. F of 1, we already know that to be 1. I mean, that's kind of what the point of having the point 1, 1 be on our graph. And we need to divide that by delta x. What is this limit? We can't just plug in 0. We can't just plug in delta x equals 0, because that's not going to work. It's actually never going to work in any of these examples. We're always going to have to do at least something before we can actually proceed, because the delta x on the bottom is always there. What we're going to do is we're going to take this square of 1 plus delta x, and we're going to expand it out. That is the square of a binomial. We can go ahead and FOIL that. That expands to 1 plus 2 delta x plus delta x squared. We saw the minus 1, and we saw the delta x on bottom. Of course, the first thing that we can notice is that we have a minus 1 here and a positive 1 here. Those cancel each other out. So the top is just 2 delta x plus delta x squared. We still have a delta x on the bottom. And now we get more cancellation. Basically, we have a delta x in all the terms on top. We can cancel that with the delta x on the bottom. Notice here that when we cancel this delta x on the bottom, we have to cancel it from every single term on the top. That means we cancel it from here, leaving just the 2. And the delta x squared, we have to cancel one of those, which means I'm just going to go ahead and cancel the square here. Basically, delta x squared over delta x is just delta x. So we have simplified this down to 2 plus delta x, or the limit of 2 plus delta x as delta x goes to 0. Once we've gotten that delta x no longer on the bottom, now we can actually think about plugging in the 0 again. Because all we have here is actually a linear function, or you can say it's a polynomial if you prefer. We can go ahead and try to plug in 0. When we plug in 0, we get 2 plus 0, and so ultimately we get 2. And that's essentially what I did to find our tangent line. So here, the line y equals 2x minus 1, that slope is the 2 that we just found. And the minus 1 I just got by using the point slope form once I had that slope. So I know it passed through the point 1, 1, and I know it has a slope of 2. That's enough information for me to derive the equation for the tangent line using the point slope form. That's all stuff that we've already actually discussed back in chapter 1. So we'll do some examples like that in some other problems later on. But the idea here is, how do we find that slope? That's the main key thing that we need to discuss first. Let's give this concept a name and a notation, so we can actually, so I don't have to go writing slope of f at x every time. We're going to call it the derivative. So the derivative of f at x is the number. Well, first of all, it's that limit that we were talking about before. The limit is delta x goes to 0 of f of x plus delta x minus f of x over delta x. but we give it the notation of f prime of x. So that's what this little you could say it's an apostrophe essentially, but it's mathematically called a prime. So f prime of x is equal to this limit, provided that limit exists. If the limit doesn't always have to exist. If this exists, if that limit exists, we say f is differentiable at x. So it's kind of a different word here, but it's just kind of a derivative and differentiable just go hand in hand. But we're saying it's differentiable, meaning that we can find the derivative. Or another way we say that. So the process of finding the derivative is called differentiation. So get used to these terms. We're going to be using them quite a bit. In fact, we're pretty much not going to stop using them throughout the entirety of the course. I mean, we'll take kind of a little bit of break from them. I think in what chapter is that going to be in? Maybe in chapter 5? Yeah, chapter 5. Chapter 5, we're going to move on to the other part of calculus. But derivatives make up the main first part of calculus. Now, we also have some other notations for the derivative. We don't always use the f prime notation here. Some other notations that we might see are df dx. That would be the name of the function. If we're doing that, we might put the of x part attached to that. Note here that this is not actually a fraction. This is not a df divided by a dx. This is just the name of the function. We also sometimes will put the d over dx part by itself and just leave the f of x here. This is useful when we're doing like d over dx of x squared, so we don't have to write down the name of the name f of x for whatever function we're starting with. If we set y equal to f of x, we also use the notation of y prime, similar to the f prime that we have here, or dy dx. Those are other notations that we have for derivatives. We'll probably be using most of these throughout the course. I'll kind of interchange with them, but I'll make sure that we understand these as we go through the beginning. Eventually, we'll kind of just switch between them whenever they're most convenient. But just be aware right now that while some of these look like fractions, they are not fractions. They are a limit of a fraction. That's what our difference quotient here is. So we have a fraction here, we take the limit, and because we are taking the limit of a fraction, we use this notation that looks like a fraction to kind of just say that's where it came from. It came from a fraction. But we cannot split up the dy and dx, or the df and the dx, and treat it as an actual fraction. At least not right now. We'll kind of come back to this at the end, I think at the end of chapter 3. But for the moment, at least, don't think of this as a fraction. Alright, so this video was mostly about just defining the derivative, getting that concept of what the derivative is really trying to do set in stone. I'm going to go ahead and leave this here, and in our next video, we'll actually work through a bunch of examples. We'll actually find derivatives for various functions and show what that actually means. So meet me in the next video and we'll actually work through some problems.